Hello, my name is Yichi Zhang, and I'm a GAN applications engineer with Texas Instruments. Today, I will be going over some layout techniques while implementing TI GAN devices in your design. Here's the agenda for what will be covered in this presentation. First, we will discuss quickly on what's special about the GAN layout. The second part is the main portion of this presentation, and we will look deeper into techniques for a better layout. These techniques will be divided into steps, and recommendations will be made throughout this section. The final section will be a demo in Altium. In the demo section, I will go over a layout with commonly made mistakes and also an example of our data card with the properly followed design guidelines. Now, we are going to look at what's special about GAN layouts. Firstly, GAN devices enable high power density as they are capable of going to higher switching frequencies. The switching loss in each cycle is proportional to the switching frequency, and in high switching frequency applications, reducing parasitic capacitance and inductance is crucial for high efficiency designs. Secondly, TI-GaN is able to switch at much higher slew rates than silicon and discrete GaN FETs, which further improves the efficiency. In high slew rate situation, the ringing and ground bounce will be more pronounced if parasitic is not carefully considered. Also, more consideration need to be put into the signal immunity with high slew rates. The third one is the thermal design considerations. As we mentioned in the first and second point, GaN will enable a higher power density design, which could make heat dissipation challenging in a small form factor. A good thermal design not only could help achieve a higher efficiency, but also allow design to achieve higher power level. Before we get into the design guidelines and recommendations, let's review some background on the parasitic components related to a PCB design. The right two figures show a discrete implementation of GaN and its driver with associated parasitic inductance. The common source inductance is the inductance shared by the power loop and the gate driver loop, which is demonstrated in the top right figure in the red circle. As the common source inductance is getting larger, the gate drive voltage and current could be significantly reduced. This will result in slower switching, which increases the power dissipation. As an example, 5 nanohenry of common source inductance increases the turn-on loss by 60%. Here, since TI-GaN integrates the driver with the FET, the common source inductance is almost eliminated, which ensures the best device performance and is one less thing you need to worry about during layout. The other parasitic inductance is the gate loop inductance, which is the inductance in the gate drive loop as shown in the bottom right figure. The gate loop inductance increases the impedance between the gate and the driver, which limits the ability to hold off the GaN device during the VDS ramp. This could lead to shoot-through, which not only increases the power dissipated in the device, but also could cause the device to fail due to the operation outside of the safety operation area, or SOA. The other effect of the gate loop inductance is that it could increase the ringing at the gate, and the ringing can cause the device to turn on and off unintentionally. With our TI-GaN's integrated package, the gate loop inductance is minimized for the best gate driver performance. Here is a quick overview of TI's GaN device. As mentioned earlier, TI-GaN has a driver integrated, which allows the best common source inductance, gate loop inductance, and also the highest slew rate, which cuts the losses by 50% compared to discrete GaN. In addition, the device comes with several protection, including the UVLO, over temperature protection, and short circuit protection with 0 external components. The bottom right figure demonstrates how the device is latched by itself under 100 nanoseconds when the current reaches the OCP level. As the common source inductance and gate loop inductance are taken care of by our TI-GaNs integrated package, the power loop inductance is the inductance we need to pay attention while designing the PCB layout. The power loop inductance is the inductance in the high-frequency power loop, which is shown on the right. The power loop inductance will increase the switch node ringing and EMI, and also the voltage stress across the GaN FET that is off. As you can see on the simulation plot on the right, 20 nanohenry of power loop inductance will have ringing up to 639 volt compared to 491 volt at 2 nanohenry. And it's essential to have the power loop inductance minimized during the PCB layout. With all this background information, we are ready to move to some techniques and design guidelines for a better layout. In the following slides, I will show you 5 steps we could follow for a better PCB design, which includes minimize the power loop, minimize switch node parasitic capacitance, considerations for thermal design, isolation requirements for both high side and low side, and designs for a better signal integrity. Step 1 is to minimize the power loop inductance. The leakage inductance is proportional to the length of the trace. Looking at the figure on the top right, our 2 GaN devices and the bypass capacitors form a high-frequency power loop, and we want to place the GaN device and bypass capacitors close together to minimize the power loop length. In the same figure, the H is the distance between the power loop trace and the return trace. And look at the figure below, the W is width of the trace. For small loop inductance, H needs to be minimized and W needs to be wide. So the second recommendation would be to use wide power bus trace with return in the layer below. The other benefit by doing so is that the magnetic field will be cancelled with each other, and the power loop inductance could be greatly reduced. The third piece of advice is to use multiple ceramic bypass capacitors, which lowers the impedance across a wide frequency range. Again, tie back to the low H we mentioned above, we want to use thin PCB dielectric layer between top and mid layer 1. Step 2 is to minimize the switch node parasitic capacitance. The switch node capacitance will essentially be added to the output capacitance of the FET. Since the output capacitance of the GaN is very small, the effect of adding parasitic capacitance will be pretty significant. From the formula provided here, the switch node parasitic capacitance is proportional to the overlap area between the switch node to the ground or the input voltage trace, and inversely proportional to the distance between the traces. Minimizing the overlap area is a key to minimize the switch node capacitance. As an example here, with careful consideration, the 50 mm² overlap area only creates 17 picofarads of parasitic capacitance. Another source of parasitic capacitance is from the heatsink. Normally, heatsink is made of conductive material such as aluminum or copper, and there will be insulating thermal interface material or tin in between to add more contact area. As shown in the diagram, the heatsink is capacitive coupled to the switch node and the ground. For smaller capacitance between the switch node and the heatsink, we generally want to limit the area of the thermal pad. This is trade-off between the heat dissipation and switch node parasitic capacitance, which we will talk about in the next slide. The other general guideline is to move the switch node traces to a higher layer, which increases the distance between the two and in turn reduces the switch node capacitance. After talking about the electrical designs and ways to reduce the parasitics, we will look into ways to improve the device's thermal design, and here comes some trade-offs we need to make. For a smaller loop inductance, we want to have a larger overlap area between the return trace and die attach pad, and also thinner FR4 for better magnetic field cancellation. However, looking from the thermal performance perspective, we will want a larger area for thermal vias to transfer heat through PCB, which means the return trace cannot be as wide, since these two cannot overlap with each other. Another trade-off comes from the switch node capacitance and thermal performance. To have a reduced switch node capacitance, a smaller thermal plane is preferred, along with thicker TIM and thicker PCB to increase the distance between the switch node and heatsink. For a better thermal performance, on the other hand, it would be better to have larger thermal plane, thinner TIM, and thinner PCB for better heat transfer and smaller thermal impedance. There are no hard rules about how much trade-offs we need to make between the two, and it generally depends on the application, such as what cooling method the design is using and how much loss will be generated. Moving on to more tips on the thermal design guidelines with our TI GaN. A general rule is that more copper and more thermal vias will help the thermal design. A thickness of 2 ounce copper is preferred for good heat transfer, and the bottom copper thermal pad needs to be exposed to reduce the thermal impedance. For the thermal vias, it's better to have plated through-hole vias with 8 to 12 mil drill size and 1 mil thick plating. Also, we need to take the thermal via coverage and thermal pad into consideration, as those are trade-offs we mentioned in the previous slide. For board thickness, 1.6 mm or thinner PCB is preferred. Additionally, other advanced board structure could be considered, such as copper inlay, insulated metal substrate, and ceramic PCB for even lower thermal impedance. In step 4, we will be considering the isolation. Let's start with high side level and power shifting. The high side device level and power shifting are critical due to GaN devices' high slew rate. For high side signal level shifting, an isolator is required since the switch node is floating. A digital isolator is recommended due to their low propagation delay. While selecting the digital isolator, the common mode transient immunity, or CMTI, rating needs to be higher than the device slew rate. Here, TI's ISO 7831 with minimum CMTI of 100 kV per microsecond is recommended to pair with our LMG3410 device family. For high-side auxiliary power supply, if a transformer isolated power supply is used, the interwinding capacitance needs to be low. And also extra common mode choke are recommended to minimize the DVDT noise to digital ground. In the second part of step 4, we will discuss the low side isolation. Since there will be propagation delay associated with the high side isolation, the low side isolator could help equalize this propagation delay between the high side and the low side signal path. Another benefit of using the low side isolator is to prevent ground bouncing, since there will be high DIDT and DVDT associated with the path. There could be a large voltage drop due to the parasitics, and the local control signal ground could be very different than the ground seen from where the control signal is generated. A low-side digital isolator could prevent this issue. However, if a low-side isolator is not used due to cost or other reasons, here are 2 recommendations. If possible, try to connect the control ground and power ground at the source of the GaN power stage, so the potential difference between the two can be minimized. Alternatively, if single point ground connection at the low side cannot be achieved, common mode chokes on the signal traveling between different grounds can be used. Now let's talk about the last step, which are the things we can do to improve signal integrity. First is the decoupling capacitor placement. A general rule is to keep the decoupling capacitor as close as possible to the pins to reduce the amount of parasitics. However, sometimes it's not physically possible to place all the caps close, and we need to assign some priority to the signals. Taking a look at our LMG3410 device family, the VNAC capacitor is the mean gate drive loop capacitor and needs the best inductance. VIN capacitor comes a second priority and followed by 5 volts and VDD capacitors. Looking at the screenshot on the right for our dot car layout, the C9 is the VNAC cap, which is right next to the IC pins, followed by C5 and C8, which are the caps for LDO and VDD respectively. Another recommendation is to keep all the components and traces on the same layer to minimize the inductance. Secondly, the ground plane shielding is also going to be needed. The control signals such as in, fault, and LPM must be protected from the high DVDT produced by GaN power stage. To do that, the control signal needs to be routed over a ground plane located on the adjacent layer. Also, we want to use low impedance Kelvin connection to connect ground plane to LMG3410 source, which is either using thermal vias or a connection very close to it. You can visualize this by looking at the screenshot on the right, where the Kelvin connection between the source and ground plane is next to the thermal vias. Moving the Kelvin point away from the source will add common source inductance coupling into the signals and cause problems. In addition to the ground plane shielding, the ground shield route could serve the purpose of reducing the electromagnetic interference as well. For signals which route close to the devices on the opposite side of PCB, they need to be shielded by the ground shield on the inner layer, or a ground shield route needs to be placed next to them as shown on the right. Lastly, let's look at the filtering to the critical signals. In the case of our LMG3410 family, the in pin which carries the input signal is a critical one. A RC filter of 50 ohm and 22 picofarad is recommended to improve the signal noise immunity. Also, an important point to mention is not to put a via on a signal trace within the heatsink area. For each through-hole via, there will be a pad on the bottom which forms a capacitor with the heatsink. With the high side voltage moving, the parasitic capacitance could cause the voltage on the signal line capacitor to move, which will cause signal integrity issues. Within the heatsink area, signal lines must be routed on the top layer, or alternatively, blind vias can be used. With the tips and guidelines in mind, let's review a layout with some commonly made mistakes. Here, Q1 and Q2 are our LMG3410 GaN devices, and we have power loop bypass capacitors on the top. Now, the power loop goes from the high voltage bus through the upper FET and then goes to the lower FET. Finally, it travels from the ground return loop on the side on the same layer and goes back to the bypass capacitor. Since the ground return loop is not returned directly underneath, there is no inductance cancellation, and the power loop inductance will be very large in this case. Secondly, let's look at the overlap between the switch node trace with high voltage and ground return trace. The yellow trace on the left is the switch node trace, the light blue is the V-bus, and the red trace on the left is ground return trace. Here you see the overlap between them is huge, which introduces a large amount of switch node capacitance, which leads to higher switching losses. Next, let's take a closer look at the power stage bias supply and control bypass capacitor. Recall that the priority we are given is VNAC bypass capacitor, which supplies the gate of the FET. Looking at pin 26, which is VNAC pin, the bypass capacitor is far away with long wire connect to it. The inductance along the path will make the supply to the gate very unstable. Also, the position for the VDD cap at pin 27 could also be optimized. Moving on to the next one, Another commonly made mistake is to have signal travels between different layers with vias inside heatsink area, like demonstrated here for the fault signal. The capacitor caused by the via could mess up the signal. Looking at the fault signal from the bottom device, it's too close to the top side, and there are no shielding traces to protect the signal. Lastly, the Kelvin connection here on the ground plane is too far away from the source, which is introducing too much inductance along the trace. Now, let's turn our attention to a good layout, which follows the design guidelines we mentioned in the slides, which fix up all the commonly made mistakes we made in the previous layout. This layout is from our LMG3410R050 which you could find from our ti.com/GAN website. First, looking at the power loop, we have the power going from the top, and then the return trace is directly underneath, which maximizes the inductance cancellation. Looking at the overlap between the switch node and the ground trace, and the total area is minimal. Let's zoom in and look at the bypass capacitors. Like we recommended in the slides, the V-neg cap is closest to the pin, as well as the 5 volts, VDD, and V-in caps. There are no signal vias inside the heatsink area, and the signal close to the high DVDT, like fault signal on the low side device, is properly shielded. Lastly, the Kelvin connection for the ground plane is close to the source of the IC, which minimizes the parasitic inductance along the path. As this layout is available online, feel free to utilize this as an example when you are trying to design your application with our TI GAN. The layout, along with other design tools such as SPICE model, could be found on ti.com/GAN. Thank you so much for your attention.